There's another, I don't want to get into the mathematics per se, but I want us to get a grasp of these quantities emotionally. And there is a very, very interesting handbook published by Robert Burnham, who ran the Lowell Observatory from 1950 through 79. And he's published a handbook in astronomy known as the Celestial Handbook. And he proposes a very provocative model. He noticed a coincidence that the number of inches in a statute mile happens to be about 63,360. And that happens by coincidence to be equal to the number of astronomical units in a light year. Now, an astronomical unit is a definition in astronomy. It's the distance from the Earth to the Sun. It's a basic unit of length within astronomy. And what's interesting is that basic unit of astronomy within a light year is roughly the same number as the number of inches in a statute mile. Very close. That gives rise to a useful coincidence. Let's build an imaginary model of our universe using that ratio. In other words, we're going to use that as a scaling ratio. We're going to 63,360. We're going to say that's essentially equivalent to 63,300. So we're close. And so we're going to let 1 inch represents the distance from the Earth to the Sun, a standard unit. Okay? And 1 mile will represent 1 light year. You with me so far? So just bear with me here a little bit. Let's build that model. Well, how big is the Sun? Well, if it's about 880,000 miles in diameter and it's about 93 million miles away, that turns out the Sun itself would be represented by a period. It's about 1/100 of an inch. In our model that we're building, we're going to have something 1/100 of an inch, and let's just imagine a period, or if you have a very sharp pencil, a very tiny speck represents our Sun. Good so far. All planets, it turns out, would then be able to be built in our imaginary model here within a 7-foot circle. Okay? In other words, Mercury would be 4/10 of an inch away from that speck. Venus would be 7/10 of an inch in that speck. Earth would be 1 inch. In other words, by definition, 1 inch is an astronomical unit. That's the definition of an astronomical unit. So we're using a 1-inch scale as we build this model. And Mars would be about 1.6 inches, and the Jupiter would be about 5.2 inches, Saturn about 9.5 inches, Uranus about 19.2 inches, and Neptune about 30 inches out there, and we get to Pluto, it's about 39.5 inches. So we call it nominally a meter in radius, okay? And so, when I say a 7-foot circle, I mean a diameter of 7-foot circle. So that's our solar system. If we built this model, we could easily contain it right here in the auditorium. Okay. Now, the nearest star to us is Alpha Centauri. Alpha Centauri, conveniently, is about the size of our Sun. Okay. Now, the nearest star is 4.5 light years away. In our model, you see, that equates to a speck, the size of our Sun, size of, say, a period on your paper, 4.5 miles away. We can't have it here in the auditorium. We'd have to, it goes, I want you to think 4.5 miles. And I want you to remember something else, if you remember the math. See, we've got 2 specks of dust that are separated by 4.5 miles. And I want you to remember that according to the Newton's universal law of gravity, you take the product of the masses and divide by the square of the distance between them. So not only is it 4.5 miles away, it mathematically has to be that squared, like 20 miles equivalent, so to speak, if you're with me. So the question that lurks in our minds, how much influence would gravity have between these 2 specks? 2 specks the size of a period, separated by the equivalent of 20 miles of distance, or 4.5 miles squared, if you will. See, what you discover as you explore these topics is that most astronomers have presumed a gravitational universe. Gravity is very useful for our solar system because the distances are nominal. The minute you start talking about stars and galaxies, gravity is a non-player. And I want you, it's amazing to discover here is a science populated by brilliant people that are victims of their own presumptions, interestingly enough. if we look at the fundamental forces, and we won't go into, I'm drawing, of course, on a series of studies. We have the Beyond Perception, the Beyond Time and Space, the Beyond series we call it. I'm drawing on some of those just to get some conclusions here. As you look at the four fundamental forces, you discover very quickly that gravity is eclipsed by electromagnetic by a factor of 10 to the 36th. In other words, electromagnetic forces are 10 with 36 zeros after it, more intense than gravity. And it works plus and minus. Gravity doesn't, we haven't found an anti-gravity force, but electromagnetic goes in both directions. So it's vastly, compellingly the dominant factor, especially as you start increasing long distances. What we've discovered in recent years is the universe that you see in a telescope. If you're talking about stars and galaxies, you're looking at electrical behavior, not gravitational behavior. We actually have what people are beginning to call, finally, the plasma universe. The plasma physicists have been saying this for years, but no one's been paying attention until recently. And we have a briefing package on that called Beyond Newton, and I encourage you to look at it if you're interested in that. The effects of gravity are minuscule on the universe. The effects of electromagnetism can be 10 to 36 times as great. The entire volume of our galaxy is filled with diffuse clouds of magnetized plasma, electrically charged, ionized particles. And they behave very understandably, but very non-intuitively. And so 99% of all matter is not gas, liquid, or solid, it's plasma. Plasma is not just a gas, it's an ionized gas. It behaves as an organ on its own. And some experiments in Europe, GEO 600 experiments, now suggest they think they have discovered it actually is holographic in nature. And that's a whole other study that goes beyond our view right here.